Let me walk you first through the presentation outline. I'll talk initially about some of the background material. What is high-strength concrete? What is high-strength reinforcement? Why do we use it? I'll talk about some of our project case histories, and then we'll talk about what the future holds. There are many talented people working in the fields of both high-strength concrete and high-strength reinforcement. A number of committees sponsored by NIST and other organizations that are doing some wonderful and very exciting things to increase both the understanding and the application of high-strength concrete and high-strength reinforcing materials. What I'll also do is deviate somewhat when I get to the project case histories, assuming that the majority of the audience are either structural engineers or people who are in some fashion involved in structural design. I'll talk about some of the project detail that I think may be of interest. And it will be relevant to the use of high-strength concrete and high-strength reinforcement, but in some cases only in a peripheral way. But again, I'm sure you'll find it of interest. All right, the advantages of high-strength concrete and high-strength reinforcement. First of all, with respect to improved constructability, for those of you involved in the design of reinforced concrete structures, and I assume that that's the majority of the audience, you know that constructability can be the bane of reinforced concrete. It's one thing to do the analytical work. It's one thing to produce the documents. It's something totally different to produce a set of buildable documents and a design that reflects a buildable structure. It's imperative that designers understand this and be mindful of it as they do their work. High-strength concrete and high-strength rebar provide some additional tools in the toolkit that can assist in improving constructability. For example, in reducing congestion, which I'll talk a lot about today as we move through the seminar, high-strength reinforcing steel can do wonders in reducing congestion, particularly in seismic elements, but also in other types of structures. And also in the realm of standardization of member sizes, for example, with columns. If we have high-strength concrete available to us in the market that we're working in, it can make it much easier, especially in a high building, to standardize column sizes, often from top to bottom. It's very possible to take buildings as high as 25, 30 or more stories and work with a standard column size from the top of the foundation all the way to the roof by simply varying concrete strength as we go up. And that all translates into a more constructible, buildable, and more cost-effective structure. Reducing member sizes. The example I used of columns is a very good one. If we work with high-strength concrete, and we also keep in mind that in designing columns, we're trying to put compression into the concrete, use the vertical reinforcing primarily for flexure, and not use vertical rebar to carry compression because it's very, very costly. If we're mindful of that as we do our work, we can use high-strength concrete as a tool to standardize column sizes, reduce cost, and reduce the member size in the process. Shear walls. High-strength concrete and high-strength rebar are finding more and more application in the field of shear wall design. The design of a shear wall very often, especially in a higher building, is controlled by lateral drift as opposed to strength. And as we all know, for those of you who are practicing structural engineers, it's one thing to make an element strong enough. It's a different kettle of fish to make it stiff enough. And they're more or less unrelated concepts. So the design of a shear wall, given that it very often is controlled by stiffness and lateral drift of the building, can make great benefit of high-strength concrete in helping to solve that problem. And then finally, in reducing construction cost, as I mentioned earlier with columns, if we carry compression in the concrete and use the vertical bar to carry flexure, we can normally create real cost economy in our designs. And in very many examples, at least in the work that we do, we'll have buildings where the lower 2 or 3 or 4 stories need just an extra dose of FC prime, basically, to avoid having to increase vertical rebar to the point that we throw excess dollars into the job. So we'll take a column that might up in the higher levels be, say, 6,000 or 8,000 psi and push it up 1,000 or 2 and we can significantly reduce the cost of the column by eliminating the need for vertical compression steel.